Hello everyone, in this video we'll be solving problem 433 minimum genetic mutation. The problem statement is we are given two gene string, start gene and the end gene and a gene bank. We need to return the minimum number of mutations needed to mutate from the start gene to end gene, and if it is not possible, return -1. A gene string is an 8-character long string with choices from A, C, G and T. By doing n number of mutations, the aim is to try to convert the start gene to end gene. In example number 1, between the start and the end gene, there is only one mutation needed, which is at the last character. You can see on the start gene we have T, but on the end gene we have A. And the destination that we want to get to exists in the bank. So with just one mutation, we can convert start gene to end gene. Hence the output is 1. I hope you were able to understand the problem statement at a high level. Let's switch to whiteboard and discuss how it can be solved. To keep it simple, I'll be using 4 characters long strings instead of 8 characters. Let's take this as our example. This is the start gene and this is the end gene. Unfortunately, this problem is not as straightforward as it looks, where we can compare each character at the corresponding indexes to identify the differences and then start mutating. It is possible that we need to do multiple intermediate mutations to reach to end. Let's extend the very same example but update the contents in the bank array. If we try to do one-to-one mapping between the two strings, it is not possible to do the mutation because the intermediate string does not exist in the bank. In this case, we'll have to try all possible combinations for all of the characters in the string and replace it with the mutated gene available while checking if it exists in the bank. Let's do a short try run with the first character A. As there are 6 genes available, from A we can try 5 possibilities. I'm avoiding the character A because it equals to the original string. With the first character changing and the rest of the string staying as is, we'll compare the new or mutated string against the bank to see if that gene exists. This cycle will be repeated for the rest of the characters too. If we stumble upon a combination that exists in the bank, we'll have to repeat the same cycle on the updated string. This will continue until we figure out the end gene or we have exhausted all possible combinations. So as you can see, the number of mutations or combinations that we will have to do to check if the mutation is possible will grow exponentially. Hence, brute force is not the ideal solution here. So now let's discuss if there is a better way of solving this problem. The concern in the previous approach is the number of mutations that we are doing is going to grow exponentially, and there is also a possibility where we'll be repeating the same calculation multiple times, resulting in an infinite loop. Let's say my starting gene is ABCD, and after doing one mutation, I get AACD on the second character. Now when we apply the same logic on the second string or the intermediate string, it is possible to go back to ABCD because we are trying all possible combinations. As you can see, with this approach, we'll be stuck in an infinite loop. As our intention is to try all possible mutations for each string, the best approach I can think of here is to use BFS traversal to identify possible strings and build more mutations on top of them. And in BFS, because we want to track which string needs to be processed next, the best solution is to use queue-like data structure. During the traversal, as we identify more combinations, we'll first check if it exists in the bank and only then add it to the queue. This is the simplified version of the previous approach, but how will this solve the duplicate issue or infinite loop issue? The simplest way to solve that problem is to use an additional array or a collection that will be marking each string as visited once we have processed it. Before adding any mutated string to the queue, we'll first bounce it against the visited array to see if it is visited. If it is not, only then it will be added. And at the same time, we'll mark it as visited in this array. Another approach to solving this part of the problem is to also remove that particular element from the bank itself. Once we know that we have identified a valid mutation, we can remove it from the bank and then add it to the queue. So next time when we encounter that same string, we will not find it in the bank, so we will not add it to the queue. Now let's do a quick dry run to understand how the queue and this visited array will help us solve the problem in a better way. Let's start with the first character A and identify all possible mutations. These are all of the possible cases that we can do by replacing the first character. Now we'll check each of them against the bank to see which one exists. As none of these combinations exist in the bank, we can't use it. So we'll increment our pointer and look at the next character in the input string, that is B. Amongst all of these four combinations, the last one exists in our bank. As this mutation is not equal to the end gene, we'll add it to the queue so that we can try additional possibilities to reach to end gene. I will repeat the same cycle for the remaining characters in the string, that is C and D. We will exhaust all possibilities of building the combinations or mutations with the remaining characters in the string, and if the updated string or gene exists in the bank, we'll add it to the queue. Once the combinations are complete, we'll then look at the queue to identify the next string available. As ABCD is the first element in the queue, we'll start processing it, identifying the combination for the first character A. I know none of these combinations exist in the bank, so I will not go into details. To avoid falling into the infinite loop trap, when we are adding the string ABCD into the queue, we will remove it from the bank. Now coming back to our string in hand, there are no valid genes in the bank if we do the mutation on the first three characters. So let's increment our pointer to the last character, that is D. Amongst all of the genes with this combination, there is one such combination which exists in the bank and also matches our end gene. As we have identified the number of mutations needed to reach to the end gene, we can stop the iteration and return it as our output. For this example, we needed 2 mutations. As the length of the gene character is 8 and each character can be substituted with 4 different gene combinations, the total number of possibilities for a single string will be 8 into 4, that is 32, which can also be represented as O of 1 as it is a constant time complexity. And in the worst case scenario, we might have to do the mutations for all possible entries in the bank. So if we say the size of the bank is n, the overall time complexity will be 32 into O of n. Substituting 32 with O of 1, the overall time complexity will be O of n into O of 1, that is O of n. While the space complexity is also O of n, as we are using an additional collection queue to maintain the list of mutated strings. The size of the queue will not be greater than the size of the bank array. I hope this explanation was helpful. Let me show you how we can implement this solution using Java. In this Java implementation, I am converting the bank, which is a string array, into a set so that I can do a O of 1 lookup whenever I want to check if the mutated string exists. After that, I am initializing a queue of type string, which will be used to record all of the mutated string to see if we can reach the end gene. To begin with, I am adding the start gene into the queue. After that, I am starting the BFS traversal by running a while loop until queue is not empty. This level variable will record the number of mutations we did so far. Inside this while loop, I am starting a for loop to iterate through all of the elements in the given queue at the given moment. Inside this for loop, I am removing the first element from the queue and converting it into character array. Now that I know which string I am going to be working on, I am starting another for loop to iterate through all of the characters in that corresponding string and saving the original character value in a separate variable before we replace it. I'm then starting another nested for loop to iterate through all 4 possible gene characters to replace the original character with it. Inside this for loop, I am saving the character into the string and then checking if the mutated string is equal to the end gene we are looking for, and also it exists in the bank set. If both of the conditions are true, it means we found our end gene. So I can stop the iteration and return the level as the output. If the mutated string is not equal to the end gene but it exists in the bank, so I am removing it from the bank set and adding it to the queue. After trying all possible combinations to replace the original gene with the new gene, I am reverting the character back to its original value so that we can try the mutation with the next string. Let's say we have tried all possible combinations and we were not able to reach the end gene. The queue will be empty and we will jump out of the while loop and return -1 as the output. This code, when submitted on LeetCode, beats nearly 84% of the submissions in terms of runtime, and nearly 70% in terms of memory. Thank you for watching this video. I hope you are able to understand the explanation. The details to access the source code is available in the description below. Feel free to check that out, and I will see you in the next one. Thank you.